All right, so let's talk about activation energy. This is going to roll right into reaction mechanisms. I don't know if I'm where I'm gonna pause, but well, here we go. So activation energy. So we've talked about these reactions occurring, but what we need to talk, and we did talk about needing some amount of energy to start a reaction. We call that the activation energy. So there's a minimum amount of energy that is required for a reaction to occur. We call that EA. The activation energy is that minimum activation required. So if we're thinking about a reaction, we can think about it like, all right, what if there is a ball on one side? What if there happens to be a ball on one side of it's like a putting green or something, right? I have my reactants over here. I have my products on the other side. In order to get this ball to the other side, it has to get over that little hump. That little hump is going to be our activation energy. We have to hit it with enough force that it can actually make it over that hump. So that is our activation energy, right? So we call this another way that we look at this is we call these reaction PE diagrams. It's essentially a potential energy diagram for a reaction, right? So what we're going to have is we're going to have energy on one axis, and we're going to have reaction progress on the other. So the reaction progress. So there's two different types of PEs that we see. Well, there's plenty of different types of PEs, but you can think about it this way. I have reactants on one side, products on the other. So reaction progress starting from reactants all the way to products. So if we look at the rearrangement of methyl isonitrile, again, remember that's just simply saying, okay, I have this nitrogen with a triple bond to carbon, and the product is going to be carbon with a triple bond to nitrogen. So what's going to happen is we're slowly going to shift. So the carbon and the nitrogen switch spots. So as our reaction progresses, I'm sorry, I'm gonna start this again because I don't love it. As our reaction progresses, right? So as reaction progresses in this direction, what happens is that nitrogen and carbon are slowly switching spots. Here at the very top, we'll talk about what this is, but this is the peak of energy. It's the highest energy state. Okay, so what we can imagine is slowly, as let's say we're halfway up this, we have this nitrogen here and this carbon there. So it's slowly starting to like rotate around. At the very peak here, we have this nitrogen and this carbon almost orthogonal. So they're essentially 90 degrees to one another. And as we start to slip down, the carbon is now starting to replace the nitrogen until we finally get to the product. Okay, so start here, starts to rotate. In fact, I did kind of the other way, it's fine. The carbon is starting to rotate away. Carbon's now equal, carbon is now bonded, and we finally have our product. So it's just kind of a slow exchange. Okay, so there's a couple of things that are important here. So first of all, there's a couple of energies involved here that we need to kind of take a look at. Let's see, let me use this. All right. So we have an energy up top. We have this energy right here. And we have this energy down here. Okay, so the energy here is the energy of the reactants. Down here, I have my energy of products. And up top, we have the peak energy or the most energy that we actually need. So this is the highest energy. This right here at the very top, this thing is known as an activated complex. It's very high energy. In fact, it's the highest energy in this situation. So this is the highest energy activated complex. At this point, it can either, the activated complex can either slide back to reactants. It doesn't need to react. It could simply, that nitrogen could slip back into spot and go back to reactants, or it can go forward to products. Okay, so I'm gonna pause this for 1 second. Okay, so I bought this little toy for exactly this reason. And so now I'm gonna just stop share for a moment. So this little toy right here, if you toss it in the air, it starts as blue. Now, if you toss it into the air a couple of times, eventually you're gonna get it to turn from one color to the other, right? So it starts purple, blue. Blue, purple, blue, blue, purple. Okay, so you can imagine that this is my, let's say this is my reactant. And as it starts to go climb, the energy is expanding and expanding and expanding until, or the energy is getting higher and higher until we have this crazy, it's not going to stay like this. This toy is never going to stay like this state in this state. This is my activated complex. So when it's spinning in the air like that, it can either snap forward to products, or when it's like this, it could just simply snap back to reactants. So activated complex is like this really high energy state, and it's either going to go back or it's going to go forward to our products. Okay, so that's the idea of an activated complex. It's just this very high energy state. Yeah, it's just a very high energy state. And so there we are. So reaction occurs, gets the activated complex, and it chills out down to products. So a couple of things that we're interested in here. So I said we have the energy of the reactants, the energy of the products. We would call the energy from reactant to the top of this peak. So this peak right here, let me use a different color for this. So this energy from here to here, okay, this is known as that is the activation energy, okay, of the forward reaction. If we put a ton of energy into this, there's actually no reason that it can't go up in the opposite direction. So this is the activation energy of the reverse reaction. So just like if I put in this much energy, it can go this way. If I put in enough energy to get it over this hump, it could actually go back towards products or back towards reactants. So we have to watch out for that. So we have activation energy of the forward and activation energy of the reverse. And the final thing that I'll say is the energy between reactants to products. In this case, this is our enthalpy of reaction. And in this case, products minus reactants, this is going to be negative. So this is an exothermic process. So this is going to release energy because the reactants, the products are lower in energy than the reactants. So this is exothermic because the reactants are higher energy than the products. Good? All right. There's no reason that it needs to exist like that. We can actually run a reaction that takes multiple steps. So we could look at the reaction like this, and in fact, I'll do the other type. This reaction, for example, I'll do some other version of that. There we go. Again, reactants, products, activated complex, activated complex. We can have two. In fact, you should probably pause this and tell me where are the activation energy? What is the activation energy? What is the so what is the activation of the forward? What is the activation energy of the reverse? And where is the what is the delta H? Is it positive or negative? And show me that those energy changes. Yeah, I would do that. All right, and now I will show you. So again, we have a bunch of different energies. The one energy that I care about is this one way up here. That's not good. There we go. Eventually I'll get it. There we go. Energy there. Energy of products. Energy of reactants. So again, this right here is the activation energy for the forward reaction, because that's the peak that I have to make it over in order to make it to products. For the return trip, I still need to make it over that hump. So that one is the difference. This is the activation energy of the reverse reaction. And the difference here between those two, this is my delta H, which happens to be positive. This is endothermic. Good. All right. So one little thing that we do need to be aware of is this spot right here. That spot right there contains the intermediates. So these things are stable because they're in a valley of energy, but they're not stable enough to stick around. You can actually detect these. Activated complexes you cannot detect, because they're, as soon as they're at that high peak energy, they're going to go left or they're going to go right. They're going to go back or forward. So these are intermediates. An intermediate is something that forms and then is immediately consumed. So we'll see a handful of these in our other examples below, but the intermediates are something that are consumed right after they're formed. Good. Oh, so I labeled it axes, energy. Again, this is the reaction coordinate or reaction progress. All right, great. So Maxwell-Boltzmann distribution, if you're a chemist, you hear this a lot. If you're a physicist, you probably hear this even more. Maxwell-Boltzmann distribution talks about energies involved, and we talk about this quite a bit. We've already talked about this, whether you remembered or not. By increasing the temperature, because the red line is the higher energy, you notice how it kind of starts to flatten out, right? The next energy would look something like this. And it kind of keeps going like that. It's not even on both sides. It doesn't look like a bell curve. We have that minimum energy, activation energy, which ultimately means that as long as the molecules, so these molecules here are the ones that are going to react because they've gotten over that activation energy hump. So the higher the energy, the more fraction of molecules we have that achieve the, so increasing the temperature equals the increase in the number of molecules with enough energy to react. So that's why higher energies typically lead to more reactions, because that fraction of molecules, and this is the Maxwell-Boltzmann distribution or Maxwell-Boltzmann equation, the fraction of molecules, the F is the fraction of molecules that can react, is equal to E all over the activation energy all over RT, where R is, again, it's an energy one, so 0.314 joules per mole K. We don't really need to know this one. It's just the idea that the fraction of reactable ones, it has to do with energy and temperature and that ideal gas constant. Yeah, and temperature, again, is always in Kelvin. So this Ardenius equation, Ardenius basically developed a mathematical relationship between our equilibrium, I'm sorry, not equilibrium, our kinetic constant K, our rate constant, along with activation energy. He said, all right, well, K is equal to some value, some constant frequency factor, he called it, EA all over RT. Don't need to know this one really either. It's just this frequency factor. And taking the natural, applying some math to it, essentially what it looks like is natural log of lowercase k, natural log of k is equal to activation energy over R, 1 over T plus natural log of that frequency factor. Again, don't really need to know that. Ultimately, what it comes down to is this is the equation. Natural log of K1 over K2 is equal to negative activation energy over R, 1 over T2 minus 1 over T1. Again, notice that the temperatures have switched spots. My temperature in Kelvin, okay? And my slope in this case, because this is in the form of y equals mx, slope is equal to negative EA over R. So we can calculate, if we can graph, and we're going to do this, if we can graph K as a function of or I'm sorry, natural log of K as a function of 1 over T, we can actually determine our slope or our activation energy. So it's a good little thing to be able to do. And we can also do it with 2 different values. So find the activation energy if the rate constant at 600 is 3.4 molarity per second and 31 at 750 K. So let's solve this problem. Let's determine the activation energy. And in fact, we have another one. So we're going to use the Ardenius equation, right? The Ardenius equation, yeah, the Ardenius equation to solve that. So again, this is the equation that you should be focusing on, one that you should understand. This equates T to, or activation energy to K and such and such, okay? And so there's a bunch of problems to do, and we're gonna move on to reaction mechanisms next.